Curved reflectors. So you can write that down. This is our new note. And again, just like when we were dealing with plane mirrors, I'm going to do a quick little introduction, just like I did with the plane mirror. We're going to talk about terms and words that we use to describe important parts of the mirror. Then we're going to stop the note, and then we're going to do some experiments to kind of discover the way the rays bounce off of them. Very similar to what we did for plane mirrors, except obviously we're going to deal with curved mirrors, all right? And we're not going to be looking for whether angle I is equal to angle R. That we know is a universal law in terms of reflection of light. Angle I is always equal to angle R, but we're going to do some labs to kind of teach us some shortcuts on how to draw rays for curved mirrors. Okay, curved reflectors. There are two types of curved reflectors, and I'm going to get you to draw this. Now, hold on for one moment. You can write down types of curved reflectors. Put number one, circular. And what I want you to write is concave or converging. And then in a moment, I'm going to switch to this, and I'm going to show you how to draw this. All right, you see what I mean? Because right now, this looks like a whole bunch of lines and letters, and I want to show you how to draw this. So only draw or write down to concave or converging. And then I want you to get your ruler out and your protractor out, and we're going to be, again, using our protractor and our ruler, and I'm going to do this then on the screen. So if you need to come up and get a protractor and a ruler, you can. There's many of them out there already, so you can just use those if you have them out there. And I'll turn this on, and we'll switch the input to this. Input. There is no other signal. You are so... Okay. You're not. It's because I didn't plug it in. Plugging it in. Input. All right. And we have our graph paper there. You can see that there. Beautiful. And I'm going to be using graph paper for this. You guys just have your regular note paper. There's nothing wrong with that for the notes. When we start to do our experiments, and I explain to you how to do the lab, you will be doing the lab on graph paper. And the reason we like to use graph paper is because in many cases, we need lines that are parallel to each other. And it's much easier for you to generate parallel lines on a piece of graph paper because there are all kinds of parallel lines already on the graph paper, so that you can make reference to them, and it makes the lab much easier, all right? With the other one, we wanted to look at angles, so we didn't want the lines to be there. So we're going to have to make diagrams in the future of curved mirrors. And so we need a way, I'm just trying to get a gauge on where everything is on my paper. We need a way in order to draw these, and the protractor works great as a curved surface. So let's use that as our curved surface. Now, before we draw anything, we want to draw a line kind of in the middle, because in a moment I'm going to put the protractor on and I'm going to make the curved mirror, and we're going to put a line on here. And actually, I'm going to use a thicker pencil today so I can see it better. So I'm going to just draw a line like so, and it would have been nice if it was on one of those lines, but it's not bad. There's my line right there. And we have a name for this line. This line, and I'm going to move it over here, is called the PA. All right? And underneath, I'm going to define some of these things. Right? The PA is what we call the principal axis. So I'm going to move down to the bottom here, and PA is what we call the principal axis. All right? So the PA is the principal axis, and it's the main line in which the light is going to hit the mirror, or it's kind of the main middle line for the mirror. Next, I'm going to draw the mirror, and I'm going to use the protractor as the curved surface. So I'm going to put that right on 90, all right? And I'm not necessarily going to draw the whole semicircle. but I'm going to just draw a little bit of it. And the nice thing about our protractor is that it is circularly curved. It's a semicircle. So this works perfect for a picture of a curved mirror. All right? And I'm going to put the markings on the back to represent the fact that that's dull. Okay? And where the principal axis meets the mirror, we call that V, and that particular thing is called the vertex. So I'm going to go back down to the bottom of the page here. V is the vertex, and it is essentially where the PA meets the, am I gone off the page yet? Not yet. Mirror. Where the PA meets the mirror. All right? Now, we have here these kind of mirrors that we're going to work with, and they're only kind of curved like a cylinder. But we're going to expand all of this to actually completely spherically curved mirrors in 3 dimensions. This is kind of like curved in 2 dimensions. We're going to talk about curved mirrors in 3 dimensions. So we will be able to extend this kind of 2-dimensional curvature flat on a piece of paper. We're going to expand it to a 3-dimensional curve, which is then like the inside of a spherical mirror. All right? And I've got some of those kind of put away. I'll show them to you later on, probably tomorrow when we get finished the labs. So this is a 2-dimensional analogy of a 3-dimensionally kind of spherical mirror. Okay, excellent. Now some important locations. It turns out that the diameter of these particular protractors are 10 centimeters, right? And what I want now is to draw a spot which is 5 centimeters from the vertex. And so essentially I am drawing to the radius of the circle. Does that make sense? Right? The diameter of this protractor, right there, see how I've got it all the way on the curve, is 10 centimeters, right? The diameter is 10 centimeters. You see there, 10 centimeters. So I want to find the center. I want to find the center of this semicircular curve. It is right there, all right? But I can't put a mark there, so I'm going to take my ruler and I'm going to put a mark at exactly 5 centimeters from the mirror. Okay, everybody catch that mark there? Depending on the type of circular curved mirror you have, it's going to have a different center, right? You'll notice on this one here that we're going to use as the lab, notice it's not as curved as the protractor, so its center will be further out because the circle that makes it, if I were to complete the circle, would be a bigger circle than the circle made by the protractor. Does that make sense to everybody, what I'm saying? All right? But what I'm drawing, though, is the center of what that curve would be, and it gets a letter capital C. And guess what? It's called the center of curvature. Ooh. Okay, you're not excited because it's not exciting. C. C is the center of curvature. And I just scribbled that at the end. You get the idea. And it is the center of the circle if the mirror was a complete circle. All right, does that make sense? If you made a complete circle out of it, that would be the center of it. Okay? And because my little mirror here is not as curved as the protractor, then its center of curvature would be further away because its circle would be bigger. okay? But it's an important part, C, all right? The next part I want to label is that distance from C to the vertex. That's one of those squiggly little thingamajiggers that kind of, you know what I mean? You know what I'm talking about? I could have did it with some, like, maybe some anyway, don't worry about it. We'll do it that way. That's called R, little r, lowercase r. So the C is the center of the circle if the mirror was a circle. So what do you think R is if it goes from the mirror out to the center? Yep, the radius, the radius. Did you hear that snap over there? That was one of my reactions that's still going on from this morning. That's nitrogen triiodide. That's still snapping back there. It'll be exciting when we're doing our lab if it keeps snapping. Just ignore it. It's fun. That reaction is producing a little bit of iodine. Every time a little snap goes off, it's going to smell clean in here. That's what you're smelling. Yeah, you're smelling the iodine that's coming from that reaction. And it was a snap. It's not a big deal. Okay, so let's define R. R is what we call the radius of curvature. All right? You'll notice I don't like the word curvature because I scribble it at the end, but you guys can figure that out. The radius of curvature. Okay? And the next important thing is at 2.5 centimeters, right there, another spot at 2.5. I did not pick 2.5 just because, but you're going to discover some of this stuff when you do your experiment. Mathematically, it's a pretty easy relationship, but I'm going to let you do some, figure it out for the lab. That is called capital F. Okay? And I'm kind of running out of the room on the bottom here, so I'm going to move down over here to the right. That capital F is called the focal point. Focal point. I don't think it is too earth-shattering to you to maybe figure that this kind of a mirror is going to focus some light. And it does. And that's what we call the focal point. You're going to discover that a little later on. Okay? So we have the center of curvature, which is at a distance of r. Now we need to designate what that distance from the focal point to the vertex is. And it gets a letter lowercase f, focal point, yeah. It gets a letter lowercase f, and it's called a focal length. So capital F and capital C are points or locations, and R and lowercase f are distances or lengths, right? Okay? And it's from the point to the thing. So lowercase f is the focal length, all right? The distance from the focal point to the mirror, okay? All right? Okay, that's awesome. And so there we have what we call a concave or converging mirror. I really don't know the origin of concave, but the classic physics teacher thing is to say, look at it, goes in like a cave. I really don't know if that's got a similar origin, the word cave being an indentation within a rock and concave being a mirror that is bent in, but that's one way to remember. Concave is in like a cave. We're okay with that? All right. Let's now talk about the second type that you can have. These are still circular, and I'm advancing the PowerPoint, but you can't see that. It's okay. And this is going to be convex. Can we see that? Convex, or they're also called diverging lenses. Oh, sorry. Oh, they're not lenses yet. Diverging mirrors. And it's still under circular. These are still circular. So what did we say? Did we say on the PowerPoint, did it say 1 circular and then A for just said concave? So this is still under circular. It's still a circle. We're just looking at the other side of the circle. Okay? So this is still under circular, and it's a mirror, obviously. We'll do lenses later on. So again, I'm going to do the same thing. Okay, that's not going to be able to stay on the screen, but you get the idea. And again, I'm going to take a ruler and I'm going to draw a line. Okay? And I'm going to take my protractor, and this time I'm going to flip the protractor this way. So that looks like this. I don't want the end of the protractor to go off the end of my line. All right? And again, I'm going to put it perpendicular to a nice line there like that. All right? And this time I'm going to put the mirror like that. And this time the dull side is going to go like this. So I'm now looking at the part of the mirror, not this one, but one that bows out. So that's always the joke. Bill Nye, you ever watch Bill Nye with some of your teachers? Right? If you watch the Bill Nye about mirrors, he says, of course, look at it, it's concave, it's in like a cave, and this is convex, it's out like a vex. I don't know what a vex is, but it's funnier coming from Bill Nye for some reason. I have no idea where vex comes from and what that means. It means it sticks out, I guess. I have no idea. All right. So this time, and I want us to differentiate. For this picture, when we're sending light in, we send light in towards the shiny part. So we're going to be having a ray come in like this. It's going to do something, and then it's going to bounce off. That's what we want to discover in our experiments in a moment. So for this guy, again, the key is the ray is coming in like this. So it's going to hit like that. Should you draw that little ray coming in? You could. That's going to then guide you on which way the light's coming. Because it can get a little confusing because the pictures look similar, but the shiny part is on a different spot, and that changes it. Just to complete our diagram, this is still the PA. This is still the V. Because I used the same protractor, except I flipped it over, the center of curvature is still 5 centimeters. C. But notice that the center of curvature is now on the dull side of the mirror, not on the shiny side. It's going to have a distance, which is going to be R. And again, I'm going to have another important point, which is at 2.5, not a coincidence, not a big deal. You'll figure it out, which is capital F. And again, it's going to have a distance to the V, which is lowercase f. Okay? So these are circularly convex mirrors and circularly concave mirrors. All right? And we're going to be studying them. It means that their curvature is made from a circularly shaped mirror. Before we go on to the lab, let me talk about different types of curved mirrors, and then I'll shut the recording off, and then I'll show you some things that you need to know in order to get ready for the lab. So let me switch back. Now, I know we struggle to find the button. There it is there. So, same thing that we just have here wrote down there. I'm actually missing an R on this picture, not a big deal. But I do want you to write this down. We can have parabolic reflectors, all right? Parabolic reflectors actually work a little better when it comes at pointing the rays to a nice focal point. I'm already kind of alluding some of the experiment. When you shine parallel rays at curved mirrors, especially concave ones, the rays bend towards the focus. It's tricky to do the parabolic diagram. Don't worry about it. Just write it down. So when I say a parabolic mirror, I mean its shape is derived from a parabola. But parabolic mirrors are very expensive to make because the parabolic shape is it's difficult to make as opposed to the circular shape, because if I wanted to make a circular mirror, all I need is a pipe or a circle, and all I got to do is cut chunks out of it and shine it up. That's a really cheap way to make mirrors, especially curved mirrors. Parabolic ones, you'd have to make the parabola, which is not as easy to manufacture as like a pipe that you could then just cut into chunks, right? So for things that contain curved mirrors, if they're lower quality, they'll contain circular concave mirrors, easy to make. But circular ones, they will suffer from something called spherical aberration, and I'll talk more about that once we've done the experiment. I just wanted to put this last little thing before we work on the experiment so that we've got the note kind of done to the point where I want it to be done. And I'm going to stop the recording at this point, and you guys can keep writing, and then I will talk about the experiment.